I'm Jason Lee from CU, and this talk will be on the Karger-Stein algorithm is optimal for K-cut, joint work with Anupam Gupta and Yuwong Lee, and these slides are by Anupam Gupta. Let's begin with the K-cut problem. Given a graph G, we want to delete the min-weight set of edges to split the graph into at least K components. Throughout this talk, think of K as a large constant, say 100. Throughout this talk, we'll be considering two canonical graph examples that shed some light on the K-cut problem and algorithms to solve it. One such graph is the cycle, where the opt is K. We imagine all the edges are unweighted, so they have weight 1. So opt is K, and that's achieved by cutting off any K edges of the cycle. And the number of such min K cuts becomes n choose K. The other example is a cycle, where opt is achieved by cutting off any k-1 singleton vertices, which has cost roughly n times k. The number of such cuts is n choose k-1, which is roughly again n choose k. So this should have been k-1. So throughout this talk, we'll be considering two main questions. One is a more algorithmic question, which is how fast can we compute the k-cut? What is the fastest algorithm that can compute the k-cut? The second question is a more combinatorics, a more extremal combinatorics problem, which is given the graph, how many min cuts can there be? What is the maximum extremal number of min cuts can a graph have? So prior is on the min k-cut problem. The most well-known result is this randomized algorithm by Karger and Stein, which generalizes Karger's randomized contraction algorithm for a min 2 cut for the min k-cut problem. And this runs in time n to 2k-2. There's a deterministic algorithm that runs in roughly the same time by theorem and has been recently improved slightly by Chihuri, Conrad, and Zhu. Earlier, last year, we've improved the constant 2 in the running time slightly down to 1.99 for a randomized algorithm, at least when k is large. And also in the same year, I have an algorithm that gets roughly n to the k time, modulo some lower order factors. But this only works for unweighted graphs. It actually only works for simple graphs, which are graphs with no parallel edges. What about lower bound? Well, turns out the min k-cut problem is at least as hard as the min k-clique problem. So one simple reduction shows that assuming hardest for k-clique, we should not be able to solve k-cut in much faster than n to the k time. Finally, from the approximation algorithm side, two approximate algorithms are known, and there's a hardness that says it's hard to go below 2. So what is our result for this talk? We essentially complete the picture and show an almost high upper bound. We show that actually there's a randomized algorithm to compute the min k-cut for general weighted graphs in roughly n to the k time. And this algorithm, like most of the ones before, the top 3 before, can also enumerate all the min k-cuts in a similar running time. So we also get an extremal bound of roughly n to the k. So what is our algorithm? Turns out our algorithm will be exactly the Karger-Stein algorithm for minimum k-cut. So we have the same algorithm, but an improved analysis. Let's first discuss Karger's randomized contraction algorithm for min 2 cut. The algorithm is very simple. We pick a random edge and contract it. Let's assume for the rest of this talk the graphs are unweighted. So it's the idea of picking an edge proportional to its weight. It's just a uniformly random edge because all the weights are the same. And we stop this when there are 2 vertices remaining. So imagine this is the original graph, and we just pick these edges and contract them over iteratively until we have 2 vertices remaining. And the min cut we get is simply going to be, we take the set of vertices that contract to this vertex here, let's color it red, and the other set of vertices that contract to this vertex here, final vertex here, we can color it white. That's our min cut. And in this case, turns out we got lucky in that we obtained the min cut, which is 3. So a well-known analysis shows that this simple procedure will find the min cut with probably at least 1 over n choose 2. And this is tight for the cycle. So what about k-cuts? How does Karger-Stein algorithm generalize to k-cuts? It's very simple. The only difference is that we stop when, instead of stopping at 2 vertices remaining, we stop when there are 2 k-vertices remaining. And then at that point, we just return a random partition of the rest of the graph, which is 2 k-vertices. And a similar analysis shows that this will find the min cut with probably roughly n to the minus 2k minus 1. Let's since we need properties of the analysis, let's quickly go over the analysis. So for the proof, imagine fixing an opt k-cut in your head, and throughout the algorithm, we'll be analyzing what is the probability of the algorithm picking a random edge inside the opt k-cut. And if it contracts such an edge, then the algorithm automatically fails because we've contracted an edge in the opt k-cut, and we cannot obtain opt at the very end. So when there are vertices remaining, for some r from n down to 2k, the probability of contracting an edge in opt is just opt over whatever the number of edges remaining, which is, so what is opt? Opt, I want to claim, is at most k minus 1 times the average of the smallest k minus 1 degrees in the remaining graph. Why is that? That's just because if you pick k random edges, if you pick k random vertices in the remaining graph, the expected min k cut of that is at most the expected sum of those degrees, which is exactly this quantity right here. And opt can only be smaller than that. Similarly, where's the number of edges in the remaining graph? Well, that's just r times the total average degree divided by 2. A simple counting argument. And then finally, the average to the smallest k minus 1 degrees is at most the average degree. So we get this inequality right here. Finally, what is the probability that the opt survives the contraction overall? Well, it's basically the product of this quantity where r ranges from n down to 2k, which can be approximated by n to the minus 2k minus 1. And note that this n to 2k, this 2k minus 1 here translates exactly down to here. So note that if we can prove, let's say if we can get rid of this factor 2 here, then we would automatically get rid of this factor 2 here. So it's really this factor 2 here, which comes from this factor 2 here, that is where we're getting this factor 2 in the final running time. So that is what we want to kind of improve and see how we can improve this factor. So how do we get rid of the factor 2? Well, let's ask, how does the Karger-Stein? So how do we get rid of this factor 2? So it's instructive to ask, how does the Karger-Stein algorithm perform on the cycle and the clique? Maybe that'll give us some intuition. So for the cycle, note that opt over number of edges is k over r, because at any point in the cycle, for the cycle graph, when we contract an edge, we still get a cycle. So at each iteration, the remaining graph is always a cycle. So opt over the number of edges is always k over r, and this k ends up translating to the exponent here. And this k is much less than 2k minus 1. And this k translates to the exponent here, k, n to the k. And we actually get that for a cycle, the Karger-Stein algorithm outputs a min k with probability n to the k, 1 over n to the k, which is much better than the 1 over n to 2k minus 1. So actually, our analysis is not tight for the cycle. What about the complete graph? Well, here, note that unfortunately, the algorithm is tight, at least for the initial graph, because the comparison in the numerator is roughly tight, and the comparison in the denominator is tight. So how do we improve that then? Well, our key idea throughout the paper is that this tight example does not show up over all the iterations, in the sense that after the randomized contraction algorithm performs a set of edge contractions, it is highly unlikely for the remaining graph to still be like this balanced clique, this unweighted clique. Actually, one more quantitative thing that we show is that after a while, for the clique itself, once enough iterations have been made, we should expect most vertices to actually have degree at least 2n, not n. So it gets much denser. That's good for us because the more edges there are in the graph, the higher this quantity is, which means the smaller this quantity is. So hopefully that would get rid of this factor too. So what is our theorem again? It is that the Karger-Stein algorithm outputs any fixed min k-cut with probably roughly 1 over n to the k. So our proof outline consists of 2 main steps. The first step is an algorithmic statement. It's a refined analysis of the Karger-Stein randomized contraction algorithm. And the second one is a more kind of an extremal combinatorics flavor statement, which connects cuts and graphs to extremal results about set systems. To more precisely, let's define lambda k bar to be opt over k. Think of this as the average contribution of a component in opt. For number 2, our statement is roughly the number of small cuts in the graph whose size is in lambda k bar to 2 minus epsilon times lambda k bar is at most linear in n. So think of k as a large constant. Think of epsilon as a constant. So this is like linear. This is just like a linear, just a constant. So this is linear. For one, we used property 2 and show that if G has only a linear number of small cuts, by this definition of small, then actually Karger-Stein actually behaves much better. This will be more precise when we get to there. Okay, so from now on, it'll be more useful to consider the Karger-Stein contraction algorithm in a more continuous perspective. So here, imagine each edge has its own independent exponential clock with rate 1 over lambda bar. In other words, it fires independently with probability delta over lambda k bar, for each interval delta, where delta is like a small number going to 0. When an edge fires, contracted. So I want to claim that this is actually just a reinterpretation of Karger-Stein, in a sense that the edges are contracted in random order. So this should be clear. But the advantage here is that for each time step, the events between the different edges are independent. So we can kind of like decouple the randomness between different edges, and consider each edge on its own. That is very useful for us in our analysis. So let us repeat the Karger-Stein analysis from the continuous viewpoint, just to develop some more intuition on how it works. So if R vertices remain at any time, so first of all, there's at least R times lambda k bar over 2 edges in the graph. It's the same analysis as before. And we contract in expectation at least the probability of firing times the number of edges in the graph. And now, if delta goes to 0, I want to claim this is like contracting this many vertices. The only case when these two differ could be when we contract a cycle, because in a cycle, we contract an extra edge that does not actually reduce the number of vertices. But when delta goes to 0, this should not happen. Essentially, we only contract either 0 edges or 1 edge. So there should be no cycle contraction. So it's essentially the number of vertices drops by R times delta over 2 in expectation. Equivalently, the number of vertices R drops by this factor in expectation. Now after t time, the expected number of vertices remaining should be at most n, the marginal number of vertices, times this factor to the t over delta, which is the number of time steps, which is n e to the minus t over 2. And that means we should stop by the time t star to be, and that means we should stop by time roughly 2 log n, because this becomes like roughly 1. Now what is the probability that a fixed min k cut survives by time 2 log n? is this quantity right here, which is e to the minus kt, which is roughly n to the minus 2k. Now there's something I'm sweeping under the rug, which is a concentration statement that we need. In other words, we need both events to happen at the same time, which means we need the first event to happen very, very likely, so that we can union bound the first event with the second event, which is itself very unlikely. This we will skip in the talk, but it's a more technical kind of argument. Now suppose let's use our statement 2, which is that there are only a linear number of small cuts of size in this range. In this case, what is the probability that a given cut of size at least lambda k bar, we're using the lower bound here, survives by some time t, is e to the minus t. And if there are only a linear number of these, then the probability that they all die out, that by time ln n, we should expect them all to die out. We should expect to be out most like, let's say, 1 left. And though ln n is much less than 2 ln n, which means that from time ln n to 2 ln n, we should expect there to be no small cuts remaining. So finally, what about cuts of size less than lambda k bar? Well, it turns out there can only be k minus 1 of these. If there are more, then those themselves will make a k cut of size less than opt, which would be a contradiction. So together with these effects, and the first fact, that by t time, I expect number of vertices at the most this. Well, that means that by this time ln n, which is again much less than 2 ln n, the number of remaining vertices, we should expect most remaining vertices to have degree at least twice lambda k bar, which is again a factor 2 more than the original Karger-Stein analysis shows. So that means we should imagine shrinking from root n vertices down to 1 at a much faster rate because there are more edges. And more edges means, in this exponential clock process, more edges means the graph shrinks faster. And it should shrink faster than what Karger-Stein's original algorithm analysis would show. In other words, it will shrink about twice as fast. So going from 1 ln n to 2 ln n, that time should divide by 2, and we should stop at roughly 1.5 ln n. And this would imply n to the minus 1.5k, probably a success. To fully go down to n to the k, we essentially want to exploit this improved bound at any given point in time, and not just from point 1 ln n onwards. And this can be done by tracking a differential equation. And again, as stated before, we need some concentration argument, and we have to do that here to show that with high probability, the number of vertices actually follows this differential equation. But again, we'll skip this for now for this talk because it's very technical. Let's now move to step 2. Again, the statement here is there are a linear number of cuts of size at most 2 minus epsilon times lambda k bar. Let's first sanity check this statement with the cycle and the clique. So for a cycle, lambda k bar is 1. It's opt over k and opt is k. But here there are 0 cuts of size 2 minus epsilon times 1 because the min cut is size 2. This also shows that this epsilon cannot be removed. If once epsilon is 0, their n squared, their n choose too many cuts, and that violates the linear bound. For clique, lambda k bar is roughly n minus 1, which means that every singleton cut is in fact a small cut. But if we take 2 vertices in a cut, this blows the cut up to size roughly 2n, which is more than the allowed size. So the only small cuts are the singleton cuts in the clique, and there are n of them. So far for a cycle and clique, this statement does hold. So the first idea is that essentially the set of small cuts cannot intersect in very complicated ways in the following sense. If we take any k over 2 small cuts and view them as sets on the universe of the vertices. So in other words, for each cut, take the vertices on an arbitrary side of the cut and view that as a subset of the universe of vertices. These sets cannot intersect in too many complicated ways, in the sense that their Venn diagram has at most k non-empty regions. Why is that? That's because if it had more than k regions, at least k occupied regions, then if we take the union of all of these small cuts, we split every non-empty region on its own, and we'll obtain a k cut of size at most k over 2 times the size of each, which is strictly less than op, which is a contradiction. Now you might ask, is this constraint enough? This constraint of sets intersecting in not too many complicated ways. Is that constraint enough on its own? That for any set system for which this holds, there must be a linear number of sets? It turns out this is false, and there's a counterexample. So we need something else, a new idea. So our second idea is sunflower lemmas, which dates back to Ehrach and Rado. So what is a sunflower? It's composed of a core, which may be empty, and a set of petals. These petals are disjoint over different petals, and each petal is also disjoint with the core. And the famous result of Ehrach and Rado says that if there are at least this many sets of size at most d, then this set system must include a sunflower with r petals. Contrapositively, if a set system of size at most d has no sunflower with r petals, then it must have a bounded number of sets. So we generalize the statement to consider sunflowers with non-empty core, and we show that if a set system of sets of size at most d has no sunflower with r petals and non-empty core, then it must have a linear number of sets. And we'll be using this statement in our final proof. Essentially, what we show is that the set of small cuts in the graph cannot have a large sunflower with non-empty core. So why is that? So let's make a minor technical assumption, which is there are no cuts in the graph with size smaller than lambda k bar. So the proof is essentially this picture right here, where we imagine that we contract the core and the petals to single vertices. Now, the graph has, again, by assumption, the graph has no cuts of size less than lambda k bar. So the vertices themselves have a degree at least lambda k bar. Now, each of these sets is a small cut, so its size at most 2 minus epsilon times lambda k bar. Here, let's say this is like 1.99 times lambda k bar. Well, the fact that the number of edges across the cut is at most 1.99 lambda k bar, but each of these two vertices has at least lambda k bar edges. Well, that means a large enough fraction of them must actually go between the two vertices. And this holds for each of the petals here, each of the petal vertices here. But then what is the total number of edges crossing from the core vertex to the other petal vertices, excluding the blue one? Well, that is 400. Say the sunflower has 400 petals, 401 petals, including the blue one. In that case, the sunflower would have if the sunflower had, let's say, 401 petals, so it's 400 petals excluding the blue one, well then the number of edges from the core to these petal vertices will be at least this quantity right here, which would violate the fact that this blue cut is a small cut with size at most 1.99 lambda k bar. So that concludes the proof and essentially shows a connection between graph cuts and sunflowers in extremal combinatorics. So finally, now we might ask. So we might ask again, what about these two statements? Are these two statements sufficient? In a sense that if these two statements hold, does this automatically imply that the set system must have a linear number of sets? Turns out now this is true, and we have a simple inductive argument to show that this is true. And we'll skip this in the talk and for time constraints we'll skip this in the talk. So for some open questions, one is, can we get a tight bound of n choose k on a number of n k-cats, where the tight bound is for a cycle? So with David Harris, we've had some additional progress and show that this bound can be strengthened to just n to the k times some constant depending on k. So not quite n choose k, but we do get rid of this little o1 and we replace it with a big O. Another exciting question is, can we get a 1 plus epsilon approximation in time that's fpt in k over n epsilon, but polynomial in n? This has also been answered affirmatively in a new recent very exciting result. And finally, can we de-randomize the algorithm? Can we get a deterministic algorithm to match the end of the k bound? And that's it. Thanks for listening.